Okay, we should be live. Hey everyone, welcome to another interview here on my YouTube channel. Today I've got a special guest. We're going to be talking about pulsar timing arrays and methods of detecting gravitational waves. So the question I always ask my guests, who are you? What do you do?
So my name is Boris Goncharov. I am postdoctoral researcher at the Gran Sasso Science Institute in Italy. I did my PhD at Monash University in Australia, and I worked on various gravitational wave data analysis, and that's pretty much what I'm also working on here in Italy as well.
So I guess the reason I brought you on was there was a press release that came out, I guess a couple of weeks ago, talking about your work with pulsar timing arrays. So I'd like to kind of just get into the underlying idea of what's going on here. I mean, I guess, we've talked a lot about LIGO and Virgo and the various existing gravitational wave observatories. So how does one use a pulsar to detect gravitational waves?
Yeah, that's actually a very interesting idea. I guess the main key term here is that the pulsar itself, and it's very, very precise astronomical instrument. So it's a bit unintuitive because usually when we think about some measurement, we consider something that is made by people, like, I don't know, some LIGO, for example, or interferometer or something like that, where we construct something to measure. However, the pulsar is something that the nature provides us with, and it's some specific pulsars called millisecond pulsars. They rotate very fast and they act as very, very precise clocks. In fact, they are so precise that their precision is comparable to those of atomic clocks when we observe pulsars over very long time scales. And that's basically what we use to detect gravitational waves. So when, let's say, when we look for a gravitational wave, with pulsar timing arrays, we look at also a special kind of gravitational waves, which are called nanohertz gravitational waves. So these are a very, very ultra low frequency gravitational waves. So essentially, what is happening is that when this gravitational wave passes through our galaxy, it changes the space-time between the stars and the galaxy, and slightly affects basically the propagation of radio pulses from these millisecond pulsars. And these millisecond pulsars are basically they're across this galaxy. So we have this network of very precise clocks, which based on time delays allows us to actually detect to search for these gravitational waves and hopefully detect them very soon.
So when I think about like LIGO and Virgo, you've got these L-shaped detector systems, and there's two of them, and now there's more of them with Virgo and more coming online all the time. And they're detecting these ripples of colliding black holes, colliding neutron stars, very, very high frequency events that are then, I guess, distorting the actual length of the arms, and so we're getting this detection. And it's it's amazing to detect these black holes that are colliding, and the question is always like, sure, you can detect, like, it's weird, you can detect colliding black holes that are hundreds of millions, potentially even billions of light years away, and yet when you ask, can you detect merging supermassive black holes, the astronomers always say, well, no, it happens too slowly. So can you explain to that, like, just why are traditional gravitation, I can't believe I'm saying traditional gravitational wave observatories, but why can those not detect merging supermassive black holes while, say, pulsars might be the way to do it?
Yeah, so that's a good question. And I guess in short, the answer is that related to the size of the black hole. So LIGO experiment and the Virgo experiment, they look for black holes that are basically a mass on the order of, like, let's say 10 solar masses. So this is how massive are the black holes that LIGO and Virgo are observing. However, when we look at supermassive black holes, their mass is billions of solar masses. And well, there is a well-known proportionality between the mass and the size of the black hole, the radius of the event horizon. So basically, I guess the more massive is the black hole, the bigger is the event horizon. So effectively, when we see two supermassive black holes merge, the radius or their separation is still too big to be in this audio band that is picked up by LIGO and Virgo. So they merge. They start merging way before their frequency is high enough to be picked up by LIGO and Virgo. So that's, I guess, the main idea.
And just give us a sense of that frequency. So like literally the ripples of space-time are rippling past you. And you know, we're experiencing them all the time right now as black holes are passing through our body. So I guess how quickly in a solar mass black hole event, how quickly are they actually, like, what is the frequency of them?
So it depends on the specific mass, but the range of the frequencies basically for LIGO and Virgo is it's basically around 100 hertz, but it can go from 10 hertz to a few hundred hertz and even 1,000. But usually, the black holes merge basically within that range, and neutron stars as well. So neutron stars, they're smaller, so they merge at higher frequencies. Black holes at slightly lower frequencies, but
right.
And as for supermassive black holes, they merge at basically around, well, they coalesce at somewhere around nanohertz frequencies. So as you can see, it's around like 10 orders of magnitude below. And we need to, well, in terms of, so I'm talking about hertz, but if we, for example, discuss the time scales, right, the nanohertz corresponds to basically decades of observations. So these ripples of space-time that we expect to see from nanohertz gravitational waves, for that we'll need to observe more than 10 years, and we already have observed more than 10 years.
So hold on. So let me just, I just want to sort of, so, you know, hertz obviously is cycles per second. So if you've got something that is, say, 100 hertz, then it is happening 100, you're experiencing 100 of these ripples going past you per second, right?
Pretty much. Mm-hmm.
Yeah. So with a nanohertz, you're experiencing, but it's not millions or billions of cycles per second. It's the other way around. You're waiting a billion seconds for one of these waves to pass over you.
Exactly.
Is that right?
Exactly.
Okay.
Mm-hmm.
And so obviously you've got to be very patient. And so you're saying that, and so what happens to the pulsars over the course of this, you know, as these giant waves are sweeping past? Are they hitting multiple pulsars at the same time? And so you're seeing this similar effect across all of them?
Yes, and that's actually precisely the feature that we're looking for. So by just looking at one pulsar, there is no way of knowing whether this effect of, let's say, delays and advances in arrival times for the pulses from gravitational waves or not. But when we observe an array of pulsars, then we expect to observe a very specific correlations between these arrival times in an array of pulsars that is specific to gravitational waves of general relativity.
Right. And so you've been doing these observations for 10 years now, and what have you found?
Well, actually, only recently there are some quite interesting results. Very somewhat expected, but also somewhat surprising. And as I mentioned, from gravitational waves, we do expect to see these spatial correlations. But of course, when we analyze the pulsars, before the spatial correlations, it's also been predicted that before actually we'll be able to resolve spatial correlations across the sky, we'll see the noise in the pulsars that will have a similar, time and spectral properties, which means that the overall amounts of delays and advances in arrival times in many pulsars across the sky will be very similar. And that's actually what we're seeing with recent observations. So starting from nanograph collaboration observations, And then also the Parks Collaboration Australia, which I work with, and recently the European Pulsar Time Array, we are observing this so-called common noise across the pulsars, which people think might be like the first signs of the gravitational background, but of course, in particularly in the Parks collaboration, with Parks collaboration, we argue that it's well, of course, everybody knows that, but we emphasize that we need to wait a bit longer to actually make sure we detect spatial correlations, because the noise in the pulsars, the noise coming from these neutron stars, rotating neutron stars, it might also introduce a feature similar to what we observe.
So, how many pulsars do you actually keep track of?
With the Parks Pulsar Timing Array, we in the data release that we used for the publication is employs 26 millisecond pulsars. And Nanograph used more than that, so they included, I think, around something like on the order of 50 pulsars, but I don't remember exactly.
And I mean, do you have to? So, I mean, with Parks, it's a steerable radio telescope, and so you're looking at one pulsar, you're recording data from it, you're then turning and looking at a different pulsar and recording data from it, and then you have to give up the telescope for someone else who's using it for some completely different series of observations. So if you had like a telescope that was observing all of the pulsars that you wanted to all of the time to collect all of the data, what fraction are you getting today?
Actually, I don't know exactly, but the fraction will be very small. So, for
Less
example,
than
when we
1%?
observe,
Like,
yeah, I think less than 1%, because we do observe pulsars basically roughly once every 2 weeks. And of course, there's limited observation time. And there's a limited, I guess, time where pulsar is in the sky. So yeah, the fraction is very small. However, the telescopes are quite powerful. So we observe for some time, we average down observations, and then we construct the so-called arrival times and their uncertainties. And based on these, we collect them over many years, and we use these data sets to search for gravitational waves.
so I mean, I guess the big question, of course, is have you detected any yet?
Mhm. So yes, no, not yet, not yet, but we are getting there.
What would it? I guess is it because the signals from merging supermassive black holes are outside the boundaries of the detections that you're able to make, or is it just that your predictions are wrong or haven't sort of matched reality yet?
Yeah, I think well, the predictions were overall definitely not wrong. So there are different predictions, but of course the physics is very complicated. And I think at this point we are getting to this area where theorists predict that we might see start seeing this gravitational background. But of course it depends on many factors. For example, there are different dynamics in interactions of supermassive black holes with galaxies, for example, and we don't know all of the physics there yet. So basically, we don't what we see with current experimental results. It's not unexpected, and but it's getting more and more interesting because yeah, the more we observe, I guess the more we can constrain the evolution of these interactions of supermassive black holes and galaxies. But of course, the scientific case for pulsar time is very solid, and we already detected the gravitational waves from compact binaries with LIGO. So we know that these binaries exist in nature. So it's just a matter of maybe a few more years before not a few, but several maybe more years. Nobody really knows when we'll detect, but yeah, it's hopefully happening soon. Pulsar cameras are very slow, so as you mentioned, it takes time.
And I guess, I mean, one of the things that I guess, how often do you think these mergers are happening across the observable universe?
Mhm. Yeah, so actually, I'm not 100% sure how often they are continuously like coalescing, and there are many of such sources because we know there are practically lots of galaxies out there. So it happens continuously even now. I don't know the exact numbers of the rays, but you know the pulsar time arrays they do not really detect the mergers of these black holes. They will detect actually the case where they coalesce, and they will merge at slightly higher frequencies. So what we do is we observe when in pulsar time arrays we expect to have observations of this this preliminary phase when they only coalesce and they will merge a bit at higher frequencies. This is basically this will be the frequencies where the LISA experiment will look into and that's where it will happen. But yeah.
So it's almost as if there are many black holes out there that are close and are already creating these very long gravitational waves. How long will they spend in this nano grav regime before they actually go into that higher frequency actual merger? Like, is it years, decades, millions of years?
Yeah, that might be close to millions of years. Yeah, that's they will spend a very long time there, and yeah.
And so then every black hole pair that is out there, you know, even if there's maybe only one actual merger every, I don't know, few decades, you're going to have potentially a lot that are in this slow process of orbiting around each other, just getting closer and closer and closer. And so instead of it being like these one individual events that cross us, it's more like this, I don't know, I'm thinking of just like a wavy, chaotic ocean with waves kind of all over the place, and you're trying to pick them up.
Yeah, that's a very nice description. Wavy chaotic ocean.
Yeah.
That's precisely
And
what is out there.
and so can you, from this wavy, chaotic ocean, can you pick out and even figure out the direction and distance where one of these events is happening?
So yeah, I think first it is expected it will detect the signatures of this wavy chaotic ocean because of the I guess the overall probabilities. But we might actually see some individual sources there too. So at some point when we'll get new pulsar time array experiments online, then they might be sensitive enough to actually pick out a few interesting individual sources. Yeah, so that might happen. That would be very interesting. But so far, I guess yeah, it's quite unlikely that at the moment the detectors are sensitive enough for this.
And so then I guess, you talked about this moment when the black holes are actually merging and the frequency goes up. So what kind of frequency would that be compared to 100 hertz, nanohertz? Where would you get to with an actual merging event of supermassive black holes?
So that would be somewhere, I guess, close to millihertz, roughly. So I guess that's the frequencies that the future space-based LISA experiment will
Hmm.
explore.
So again, millihertz. So you're looking at thousands of seconds for these waves to pass over. So if you, but it seems like I mean, is there a reason why you wouldn't be able to detect these millihertz events in pulsars? Like, is there? I wonder, like, why does it have to be the really long ones? Why can't it detect more frequent events?
So that actually partly has to do with some data analysis specifics of pulsar time arrays, and partly with the fact that pulsar time arrays do not observe pulsars frequently enough for millihertz frequencies. So that's one part. The second part is that at these frequencies, the pulsar time arrays, even if they observe the pulsars that often, their sensitivity would be not really not really useful there. So I guess just by design, this I guess the time and array measurements are I guess they're more sensitive when we observe long periods of time. But if we, for example, draw a sensitivity curve for pulsar timing arrays, for example, for this measuring this gravitational strain of space-time, basically by design of the experiment, the sensitivity goes really high at high frequencies, so it's not really useful there.
So does a bigger telescope get you a more precise measurement, or can a small telescope do you just get whatever the clock is telling you, or do you need to have a bigger telescope like Parkes or even say FAST to be able to make a more accurate detection?
Yeah, I think to make a more accurate detection, what helps is really, I guess, two factors. So first of all is this so-called measurement error of the telescope, and the lower is the measurement error, of course, basically the lower is this noise level that basically for measuring this gravitational background. So that's one thing that affects our detection prospects. And the second one is the number of pulsars in the array. There's actually the third one, and the third one is that the pulsars themselves, because we use them as in our measurement, they introduce measurement errors and they introduce noise, in fact. And we know, like the reason also why we don't use, for example, regular pulsars is, well, one part is that because I guess they are intrinsic properties, but in terms of like the overall, the pulse size, for example, because the wider is the pulse, the less precise we can measure the arrival time. But the second, over the long time scales, the pulsars also have the so-called red noise. And that's also, that's kind of noise that looks similarly to gravitational waves. So we basically, when we observe pulsar for like 10 years, we see that with this red noise, that at some point, like first, let's say 5 years, we see a delay in arrival times, and then the second 5 years, we see an advance in arrival time. So this is might be associated with the irregular rotation of the pulsar over this long periods of time. So that also affects our measurements. Of course, if we get like a more sensitive instrument like SKA, for example, square kilometer array in the future, it will put down the noise for the pulsars. But of course, if pulsar has red noise, then it will still not be, I guess, it won't be very sensitive to gravitational waves as the pulsar with better intrinsic noise properties.
Now you said that you don't want to use regular pulsars. So, like the slower pulsars, you like the faster pulsars?
So yes, by regular pulsars, I mean the slower pulsars. In pulsar timing arrays, we use the so-called millisecond pulsars. Because the rotation period is somewhere around a millisecond, so they rotate very fast. Basically, you can see millisecond is in fact the fastest pulsars, they rotate like around 700 times per second. So you can imagine basically like a star with size of a city rotating 700 times per second. It's it's a very extreme system.
And I guess how many of those are available to us to observe?
Well, potentially there are, I guess, well, from the numbers in current pulsar timing array experiments, we use around, let's say, like from 25 to like 50 to possibly 100 pulsars that we can use. But of course, all the brightest pulsars, they were already discovered. So I guess the new experiments, they will find the fainter pulsars, and if the pulsar is faint, then it also limits its ability to be useful to detect gravitational waves. So there is some kind of like a balance there between finding more pulsars and actually like relying on pulsars that have very nice intrinsic noise properties and very sensitive and good timers.
It's interesting. So like I've been reading some news coming from China's FAST telescope, and a lot of their work is just finding pulsars, and they've been announcing many new pulsars. And so I guess some of those are usable for them. So I guess that's very helpful for them to be churning up new pulsars that you can then use to expand the array.
Yes, that would be great. I mean, if we can add more pulsars, and so that would be really useful for resolving the so-called spatial correlations that I previously mentioned. That this basically the spatial correlations is the main signature of the gravitational wave background. So this is the smoking gun. If we detect the spatial correlations, that's basically the detection of the gravitational waves. And the more pulsars we have, the more in the sky, basically the better we'll be able to resolve these spatial correlations.
So I guess, you talked about the fact that maybe you're observing the pulsars for like one fraction of a percent because obviously there's limited telescopes and they're busy. But let's imagine that sort of a next generation pulsar timing array network was developed, which was a one dish directed at each pulsar, and they were just making continuous observations while they were up in let's put it in space, and then they're just continuously observing these pulsars nonstop, maybe one per pulsar. What do you think are the limits of this technique? So if you had that capability, would it get you to where would it get you?
Yeah, that's a good question. I think, well, the limits probably are related to, I guess, the overall, our ability overall to use the telescope time and, of course, the computational constraints, because if you have that much data, it will be really, really hard to process all of this data.
There are no limits. You have a gigantic, you have as much supercomputing time as is necessary to process the data. And there are no limits on the telescope time. You've got each pulsar, each telescope is named after its pulsar, and that's all it looks at all the time.
So in that case, the limits will be linked to, once again, the intrinsic noise properties of the pulsar. So, of course, if the pulsar, for example, it has like, in pulsar timing arrays, we discuss the so-called jitter noise. It's basically the intrinsic noise of the pulsar associated with this pulse profile or the width of the pulse. So, of course, like we can't measure individual pulse better than this pulsar already provides us with, right? Because it's, the physical, it's associated with this beaming of the pulsar, and we can't do any better than that. But of course, I think with, for example, the new instruments like the Square Kilometre Array and even the Meerkat, which is the telescope in South Africa, which is the precursor for the Square Kilometre Array. So these experiments really get us down to this intrinsic noise levels of the pulsars themselves. So the telescope basically noise is not becoming important anymore. And as you mentioned, like this is the similar cases you mentioned where we are limited by basically the intrinsic noise properties, and they provide some really, really nice and really exciting results where the timing precision for some of the pulsars gets really low, and gets very nice, and the measurement area gets very low, and these would be amazing for gravitational wave searches. And I mean, for now we observed only like for a few years with them, but when we observe for longer periods, we would have some really nice constraints and maybe even like see the detection of nanohertz gravitational waves with these new facilities, because they're really precise.
And I mean, I guess what I'm driving at is like the next level after detecting merging supermassive black holes is to try to detect the background gravitational waves of the universe, essentially the ripples left by the Big Bang and inflation. Do you think that a upgraded pulsar timing array gets us to this point that we are detecting the Big Bang itself?
Yeah, that's a good question. I think that, like, honestly, I think that might be very hard to do, and it will depend on the model of this primordial gravitational waves. Some models predict there will be signatures, there will be basically a background of these gravitational waves left over from the very early universe that will be detectable by pulsar timing arrays. But unlike the science case for supermassive black hole binaries, which is very solid, the science case for the inflationary gravitational waves or other early universe gravitational waves, it's not as solid because there are different models, and they predict different backgrounds, and some of the standard of these backgrounds are much lower than the noise levels that we can possibly get with pulsar timers. Of course, if we're lucky and if there was some interesting physics going on in the early universe, we could see these gravitational waves, and that, of course, like that would be like very exciting, and we will learn so much about our universe this way. But this is like not as solid science cases for the supermassive black hole binaries.
Well, I like this idea. I mean, like, as you mentioned with Lisa, the next step that I've heard proposed to go beyond LISA is like a one that's 12 LISAs all flying in formation, and that would be the Big Bang observer, and maybe that would be the version of an interferometer that gets you all the way back to the beginning of the universe. But if there's a natural way to just use those pulsars that are right there, and you don't have to fly 12 spacecraft in close formation, that would be great. So then, like, let's imagine that you could see the universe in gravitational waves as precisely as we can see it in visible wavelengths or infrared, right out to the edge of the observable universe. What kinds of events would we be able to see? What would that be able to tell us?
You mean in the early universe?
Just across the universe, like I'll give you an example. Like when you look at the universe in X-rays, you see the hot interstellar gas surrounding galaxies. You see the intergalactic medium. You see certain features are far more visible. When you look at the universe in radio waves, microwaves, you can see the cosmic microwave background radiation. And so if we could look at the universe and see just gravitational waves, what would we see? What would it look like?
Mm-hmm. Yeah, I think first of all we would see this. I guess the one good example is we'll see something that will be a very significant source of both signal and noise in LISA experiment, and that's the so-called the foreground of white dwarf binaries in our galaxy. So we'll have basically this white dwarf stars orbiting each other, and they will produce this gravitational waves in the millihertz band, and I guess the space around us will be filled with this radiation of like space-time wobbling from these binaries. Of course, when we go farther away from our galaxy, we'll see also in our galaxy what we might see, for example, the neutron stars, and under certain, let's say, magnetic fields and under certain conditions, they might slightly deform. So they might not just be spherical, but they might be like have some kind of like a bump on them, or their internal structure might be different, like non-uniform. So these galactic neutron stars, they will rotate, and basically by the emission of gravitational waves, the structure will tend to be more spherical again, and we'll see these maybe more, of course, more faint gravitational wave emission, but also at different frequencies, because this will be, I guess, more like LIGO-related frequencies. So then, as we go farther away from our galaxy, we'll see this LIGO signals, LIGO-Virgo signals with compact binaries merging. So we have black holes and neutron stars coalescing, merging, and then producing this radiation traveling from all over the universe from us. So then we'll see supermassive black holes, and we have merging galaxies. Then the supermassive black holes with billions of solar masses at their centers, they coalesce and merge, and they produce slow frequency gravitational waves. And of course, there will be the background, this hum of radiation, and there will be some individual sources on top of that. So it will be like something like that. And of course, from the very early universe, we'll see possibly this primordial gravitational background that will be, it is expected to be across like many frequencies. So it will be at different time scales, right? Happening like this waves will be at different time scales, but they will be very, very low in amplitude, so it will be very quiet overall. So that would be like I guess the most distant events in gravitational wave radiation that we could see.
That's really cool. I really like that sort of picture in my mind. I'm kind of imagining this totally different universe seen by mass interacting as opposed to things shining, which would be really fascinating. If you could then overlay that vision over top of the existing observations, like push it into the multimodal process, what big, outstanding questions in astronomy could we then answer?
Even by combining the gravitational wave observations with
Yeah,
the
like
like
if
electromagnetic.
you took that beautiful vision, that image of the all sky image of the gravitational wave happening, and you knew the distances, and then you overlaid on top of that the kinds of certain, the Hubble deep image and things like that. What there are all these controversies, questions that we have in astronomy, like how fast is the universe expanding, and things like that. What kind of answers could we get out of putting those two regimes together?
Mhm. Yeah, it's an interesting question, and we can get many useful answers from using gravitational wave observations. So, for example, as I mentioned, the neutron stars themselves, they can emit these gravitational waves, right? But of course, we can't look inside a neutron star. There's no way of accessing this information. So, with gravitational waves, by detecting these gravitational waves, we'll be able to look into these very dense objects. When we also, for example, look at very far away distances in the universe, then, for example, and look at binary mergers of binary neutron stars, they do produce these gravitational waves, and they also do produce electromagnetic signatures. Like, for example, for this first binary neutron star merger, where we have this kilonova emission, which is optical, right? And we have this gamma ray burst, and basically these they provide a lot of useful insights about the physics inside this object, but also by collecting this information from all over the universe, we'll be able to, for example, measure the Hubble constant very like in an independent way from current cosmological observations, because we can measure the distance from gravitational wave signature, and we can measure the so-called redshift from electromagnetic observations. And the redshift is basically like how the wavelength of light changes when it flies from the source to us. So by doing this, we can do precision cosmology, for example. And of course, with primordial gravitational waves from the very, very early universe, this will be probably the only way to study the physical processes that happened back then, because the earliest light that we can see is this cosmic microwave background radiation. It's basically it's from the time in the universe where the universe was stopped being basically very dense and started to allow the light to pass through. And this is the first light that we can see, but we can't see the light before then, because of course the universe was like super dense, and no light would reach us from there. So gravitational waves, because they could overcome this obstacle, it's the only way for us to learn about the early universe that was happening there.
Yeah, that actually sort of leads into my next question, which is that there is this time, the cosmic microwave background is 300-ish thousand years after the Big Bang, and before that, the universe was opaque, and so there was no way to see any light. And so, and really, gravitational waves are the only way to look into that time. And what do you think that we could see, maybe in more granularity? Like, what would we see in that period?
Mhm. Yeah, I think it's for now, it's very hard to say, because I guess we haven't done that yet. And there, of course, there are different models that predict different kinds of gravitational waves. We might be able to see even it is predicted we might be able even to see some gravitational waves that left over the transition, so-called phase transitions, which were basically the periods of this short periods of time where the universe went from one state to another. And by the states, I mean, for example, the transitions where physical interactions that we know at the moment, let's say the electromagnetic observations, the nuclear forces, they were more general, and they basically were more like a unified force back then. And like these kind of transitions we might be able to see by gravitational wave observations. We might be able to see gravitational waves from inflation, which is this period of very rapid, like super rapid expansion of the universe at the very, very early times. And for now, the evidence for inflation is so far is quite solid, but it's indirect. But the gravitational wave observations might be the way to actually look into these processes from another perspective, and using different methods.
And I guess one additional one is if primordial black holes are a thing, perhaps we could see them merging in this period.
Yes. So yeah, that's also interesting because it is expected. Well, the black holes that we discussed so far were astrophysical, right? So these are the black holes that formed from stars. The supermassive black holes, on the other hand, they are very big, right? And they're at the centers of galaxies. So there are some theories that suggest that maybe there's supermassive black holes, their seeds, like their initial state was a primordial black hole which formed before the first stars in the early universe, and then accreted matter, for example, like collected, grew bigger and bigger, and formed supermassive black holes. So yeah, that is one thing that we can see with the gravitational waves. Actually, not related to pulsar time and arrays. Just by LIGO Virgo observations in the future instruments that will be built after LIGO and Virgo, we might be able to look very far in the universe at very large distances, where basically we'll be able to probe the distances where even comparable to distance where the first stars in the universe formed. So, and actually, if we detect any black hole mergers from that far away in time, we'll be able to conclude that these black holes are primordial because no stars were able to form at this very large distances.
Right. I mean, I know that one of the mergers that was detected by LIGO is theorized to be a primordial black hole because you can't get a black hole of like one of the masses by any known astrophysical process apart from, like you should get either a more massive black hole or a less massive black hole, but you can't get one in this specific mass range. And so it's kind of fascinating to think that maybe these things have already been detected, if they're out there.
Yes, so there were different discussions and publications. I guess it's a very active area of research at the moment with all these LIGO detections. The scientists debate what is the origin, and there are different models. So it's I don't think there's I guess it's yeah, and even the standard population models for stars and black holes, they're also under development. And from one side, the theorists try to make a perfect theory that describes everything, and from the side we have observations. So it's all growing together to make a coherent picture of what's going on.
Yeah, it's absolutely fascinating. So would the detection of the gravitational waves using the pulsars tell you anything about the pulsars themselves?
Well, we probably not the gravitational wave detection, but of the observations of pulsars, they do. Yes, they do tell us a lot about the pulsars themselves, and there's also lots of interesting research that just even we can do with timing pulsars and measuring their arrival times, and linking these measurements to the models of what's inside the neutron stars. And for example, one of the work that I did during my PhD was actually observing this noise that is associated with the pulsars themselves, and just trying to discuss whether this noise might be from like associated with the superfluid turbulence in neutron stars. So this turbulence basically exerts some extra torque from the core to the crust of the neutron star and basically affects its rotation. So there are different models, but that area is also like an active area of research. And in fact, there are not a lot of models there. Like this is the area of physics where even there are not a lot of models because neutron stars are very complex, and it's very hard to model these things.
Well, I know there's an instrument on board the International Space Station. I think it's called New Star that detects X-ray blasts coming from various neutron stars, and it's theorized that it's happening when they're essentially shrinking a little bit, or their crust is shifting, or they're having some kind of quake inside the star. So it's definitely, there are other methods to try to detect, but it's sort of like at the using X-rays instead of gravitational waves, which is kind of a fascinating idea. Well, it's been a great interview and really exciting technique. I love this idea of using something that nature has provided to learn more about nature itself. If people want to keep track of the work that you're doing, stay tuned on the latest advances when they finally make that detection, where should they go?
Sorry, what do you mean?
Where should people to follow more if they want to go on the internet
Oh,
and see what you're doing? Where should they? What's the best place to track your work?
oh yes. So I guess one way is the website that I have. It's in the link, I guess,
Yep.
on YouTube. You already added that. So that's maybe also on Facebook or on Instagram. So these are the social media that I use.
Awesome. Okay, great. And well, thank you, Boris. Thank you so much for taking the time to chat with me today. It was awesome. I really appreciate it. Very exciting, and I can't wait to hear about the detection of of this background of merging supermassive black holes. It's pretty great.
Yeah, thank you very much for hosting me, Fraser. It
All
was
right.
nice talking to you.
All right. Take care. Thanks.
Take care. Bye.